Good morning, everyone. Well, looks like people are slowly returning after Christmas to work. It's a pleasure for me today to introduce an old friend and colleague, Carlos del Burgo, who most of you know quite well. He did his PhD here a while ago, and after here he was on a tour throughout Europe.
Very long tour.
Working in many places. He was, I think, in
Paris, Heidelberg,
in Germany,
Pisa,
in
the Netherlands, Ireland, Portugal,
Ireland,
Mexico.
Portugal. And now for the last few years, he's been as a researcher at the INAOE in Mexico. And well, he's been working on many things along his career. Started on astronomical instrumentation, mainly on multi-fiber spectroscopy here, and then work on the interstellar medium, low mass stars, galaxies, and in the last few years he's been more focused in planets and spectrophotometry in particular. So we're going to hear from him his latest research on a few stars with planets. Carlos, welcome.
Okay, Carlos, thank you very much for the introduction. Thank you very much to the organizers for inviting me to give this seminar. I hope you enjoy it a little bit. And well, let's go to the point, although I will do a brief introduction and then a relatively long introduction, and then I will present the results of this research that I am doing indeed together with Carlos Allende. So, well, the title is quite long indeed, as long as my journey, as Carlos presented, more or less. So, the characterization of the stars with and without planets from absolute flux spectrophotometry obtained with the Hubble Space Telescope. Well, let's start with the motivation. No? Although now the exercise of this research is valid by itself, so we are very happy with the results, and we will continue independently on the successful of this initiative that we had like 7 years ago. When Carlos was in London, I was in Ireland, and we meet together and consider the possibility to develop a high precision spectrophotometer to be installed in a space satellite, a satellite that is small, relatively small, a microsatellite. I will show you a little bit about this later. Well, this was the idea, so to obtain high precision spectrophotometry from space. And well, eventually we were selected in the context of an initiative that was taking place in Japan in 2013. The idea was called Pre-MIC 3 Mission Idea Contest. Well, anyway, what they wanted to do was to develop initiatives to have nano and microsatellites with a relatively low, basically, budget. No? And we were selected together with other 4 projects and presented the project in this context as a user participant. And well, it was a very nice experience. We met a lot of engineers there, and it was very exciting. But anyway, just like a highlight of the project. And this is a small sketch where you can see the science payload. I will point it here. This is basically half of the microsatellite. This on top. This is a sketch of the spectrophotometer. There are 3 mirrors. They are off-axis. This is somehow challenging. I will not go into the details, but just to give you a very brief idea. No? The science payload is about 20 kilograms, sorry. And the challenging point here is to achieve a very high, very demanding pointing stability of about 0.2 arcseconds in order to fit to the science requirements of precision of 1 millimagnitude of a few millimagnitudes. Well, we presented the optical design in 2010, and the optomechanics was developed in the framework of a thesis, Denise Fatter from Ireland, And well, the drivers of this design, just very few ideas, no? To minimize the stride light, achieve the pointing stability that we mentioned before of 0.2 arcseconds, and putting everything together with basically as a low cost. I will not give a final number, but think about a few million euros, not pesos anymore, because you know it's going down and down. It's a bad joke, but just because somebody asked me about that a few minutes before we started. So, well, sorry. Just a few ideas about phases in terms of the calibration. Here you have in white the observation obtained with the Hubble Space Telescope. This is basically a STIS and NICMOS in the infrared, STIS in the optical part. And you have in red the best model we feed to the data. It's a Kurucz model, basically, with well, many refinements that Carlos Allende did. And here you have the residuals. You can see this band at 1% and this line that corresponds to 2%. So you can see the residuals are very well confined in the optical range of phases, which is about 317 nanometers to 960 nanometers. Well, so we could reproduce very well the spectra, and we could respond positively to the science requirement of phases using the Hubble to say, okay, you can achieve certainly a very high precision, and you can be successful with this purpose of getting 1 millimagnitude just with a series of spectra. No? The idea is to get the same spectra during basically a couple of hours out of transit, also during the transit, and through relative spectrophotometry also derive the properties of the planet. But anyway, this is something that I shall develop in a different talk. So just to introduce the research we're going to see here today, this is basically what I would like to tell you. So now the introduction about the talk itself. Well, I will start saying that the main point is that, many people require to determine stellar radii with very high accuracy. And this is something you can do in different ways. I'm going to present here the way we use, because we think is the best possible, particularly for bright stars, not the brightest, but certainly bright in terms of from 2 to 10 magnitudes in the visible. But in principle, to determine the stellar diameters, you can use different ways. Now, for instance, interferometry is a very successful technique to derive angular diameters, and then in combination with parallaxes, you can derive the linear radii of the stars. No? However, as you probably know, this is limited to relatively nearby and bright stars. So therefore, it's a challenge to do interferometry for many stars, particularly for stars relatively faint. Well, so alternatively, you can derive these angular diameters using a technique which is based on the use of absolute flux spectra. In combination with models, you use the best possible model to fit the spectra, and then the ratio is going to provide you what you need to determine the angular diameter. And again, with parallaxes, you derive the stellar radius. So these are two techniques to take into account. Well, concerning parallaxes, you know that, well, it is better to go to space because you can, overcome different problems, and in particular distortions due to the Earth atmosphere. So Hipparcos in the past, and nowadays Gaia, they are very useful to do this exercise. Well, then now I will talk about basically the main target of this talk, which is HED 209458. This is a nearby a star very similar to the Sun in terms of properties, spectral type, the age. So basically everything that you may think about, affecting temperature, etc. We will see details later, of course. The point here is that, well, you have already a very high precision angular diameter determined with interferometry, with Chara in particular, and this is the value of 0.225 milliards seconds. So it's a very high precision value for this star. Well, they found some, or they mentioned in the paper, Boyajan et al. 2015, that there may be some issues because the calibrator they used was not so appropriate for this star. However, we will see that this value is really consistent with ours, although we determine this with a better precision. Well, why this star is very interesting for us and why we started with this sample to illustrate the technique, simply because it was the first transiting planet discovered in 2000 by Chabourneau, and, well, it is the only example, together with another transiting system, HD 189.733, where you have dynamical masses for both components, the star and the planet, and you derive them in a similar way to the eclipsing binaries. So, well, what you have for this star in terms of data set that was very useful for us was, again, Hubble Space Telescope. You have STIS, different ratings, and also NICMOS, and then you combine them, and indeed it was done already by Ralph Bolin in CalSpec, which is the calibration database of the Hubble. Here you have the link if you are interested in having some useful data for your research. So we use that together with the methodology we require to determine the best fitting possible to the data. And this is something we do with Ferré. Ferré was, well, it's an application developed by Allende Prieto et al. 2006. You have other references. I took just one of them. And also the link where you can download the package. And we use, there are different ways of doing the optimization. So I'm not going to describe extensively this package. This is something that probably Carlos has done already, or will do eventually. But just to mention that we use the unconstrained optimization by quadratic approximation algorithm to optimize, to determine the best fitting. And also because you have, well, a limited number of spectra, a 13 grid of models, we use, in order to interpolate, a cubic Bézier interpolation. So this is pretty much the description of our tool. And then here you have the result. So again, in black, you have the observed spectrum, well, together with some parts that correspond to models from CalSpec, but basically this range is real data. Real data observed with the Hubble. And then in red, the best fitting. And the zoom corresponds to the worst part. I don't know if this is working anymore. Yes. Well, here, this is the worst part. As you can see, basically in red here, you have the uncertainties provided by the header of this CalSpec spectrum. And, well, here you see the residuals are pretty big, just because it's very difficult to mimic the ultraviolet part of the spectrum. Now, for different issues, in particular, it's not so well understood in terms of abundance is the ultraviolet. However, in the optical and the near-infrared, the residuals are really small, and indeed the uncertainties in the CalSpec spectrum are, well, obtained is an estimation, but certainly it's an overestimation by a factor of 3. But in the ultraviolet, they are underestimated somehow, or better said, it's a problem of the models. Sorry, it's a correction I do myself. Well, so what we use is basically Kurucz-based models, together with some, well, modifications I highlighted before, that Carlos performed that. Is a synthesis code called ASSET, and you have different references to go into details. Well, in terms of abundances, you use also, well, absolute et al. Values. Well, what we achieve is just there in terms of the parameters. You have the effective temperature of 6,000 roughly Kelvin, log G 4.38. So very similar to the sun, indeed, the solar metallicity. This is just other values like the alpha and the turbulence. Well, what we do with this is just, well, a good fitting. I'll say we can be happy with that. But what we want to derive is something else, is the angular diameter properly. So I will just mention briefly something that is further developing in a paper that we published in 2010, Del Burgo et al. 2010, where we mentioned that even if we consider a huge uncertainty in all these parameters, and you play with different other fittings that are not just the best, you are going to derive a very similar angular diameter value, which is very good because it gives you the confidence that the angular diameter is nearly independent. So here is what you see, is the ratio of fluxes, the one that you derive on Earth, basically, although the Hubble is not particularly on Earth, but you know, very, very far from the star, basically at the same distance as Earth itself. And the model. So from these ratios, you have a very consistent value for the angular diameter because it's pretty much constant at Sul B, just because the model is very good. Again, you see the problem in the ultraviolet. We use the range that is between these point dash lines. Here, I think this is not working. And our value is on top. You see the uncertainty, 0.0017. The value is basically the same as Boyajian obtained with a very different approach, as I mentioned, interferometry. But the uncertainty is a factor of 4, a bit more indeed. So our technique, at least for this example, is better, and we have proof that this is not only for this, of course, it's quite general, as I mentioned, for a certain range of objects. For the very bright ones, interferometry is probably the best. For something like Vega or something like this, is already just the limit where both techniques have similar values for Vega, but below Vega is better the interferometry. Well, so I didn't mention, sorry, that Cassegrain, also with the same data set as we have used, CalSpec, they obtain a value which is very is consistent with the other two, of course, but the uncertainty is a bit, somehow 2.5 hours, because the model they used was not so good. It's just the summary. Well, then there is a different approach also to determine the stellar properties. You can use evolution models. Probably many of you are already familiarized with this, so I will just give here a few ideas. The models we use are obtained basically from the Padova school. They are called Parsec, the version 1.2s. Bressan et al., Chen et al., Tan et al. For the references. So we determine the photometry from CalSpec itself and derive the color V minus V, the absolute magnitude in combination with Hipparcos. And then I will mention what happened with Gaia, the update with Gaia, with DR1 and eventually with DR2 next year. So, well, what you have here basically is just a sketch, no? So you use absolute magnitude, the color, the solar metallicity, because this star is very similar to the sun. It's very good that it's very similar to the sun because we calibrate it against the sun. So we reproduce the data of the sun with the stellar evolution models, and if not, we introduce the shifts necessary in order to achieve this constraint. No? So the stellar models are going to mimic the values of the sun because we force to it. This is a small correction. I will not go into details, but this is what we do. And we are now testing the validity of the evolution models like many other people did in the past, but we are doing slightly different techniques to be, well, in different positions of the HR diagram, no? Not only in the vicinity of the sun. This is something that I could present eventually in a different talk, or maybe Carlos, who is here and could do it. So this is just the results that we obtain with the different approaches that I mentioned before. So ignore the third column with all these abbreviatures. I will just give you a brief indication. Now it will be handy if I have the lecture is not working anymore, right? Okay, so basically the first four values correspond to the effective temperature. So you have the best fitting, then the combination, as you see with the formula on the right of using the angular diameter with the volumetric flux, and also the value with the evolution model, and they are pretty close to each other. The uncertainty is low, but is something that you can trust in this case, because it's quite consistent for all the different values. The angular diameter that we presented before, then we use the Hipparcos parallax, and we derive the linear radii with the different approaches. Well, with the evolution model, of course, is independent on the parallax. So you don't need it. And you get a very consistent value, similar uncertainty. Then again, with these techniques, basically we derive also the stellar luminosity, and again, a very good correspondence, the absolute magnitude, well, the volumetric magnitude, the gravity, also with different techniques. In particular, I will mention this because it's quite important, and probably I see some experts of the field. So sorry for the very bad figure for the transit, but you can see that there is a very famous curve obtained with the Hubble, also by Brown et al. 2001. The Hubble was not thought to study light curves, but it was pretty good. It was by far the best light curve for this star for quite a while. And even now, I will say Kepler is pretty good, but Hubble is still excellent, no? For a very long term, you can do this kind of exercise. For a long term, it's impossible, not only because of the many programs that you have to do with the Hubble, but also because of the monitoring. Probably it will have some difficulties, but these are technical details. The point here is that you derive the depth. From the depth, you have the ratio of the planets to the square, the ratio to the ratio of the radii of the planet against the star. And you can derive also from the light curve the stellar density. And this is pretty handy because with this measure, which is quite, is very well constrained, very accurate, you can determine with the radii the mass of the star, no? When you have a very good estimation or very good determination of the radius, together with the density, you have the mass. This is what we did, so you can compare with the evolution model determination, and again, the result is relatively good within the uncertainties. However, you have 1.26 from the light curve together with our best fitting, and with the evolution model you have 1.12. Well, still within the uncertainty, but this changes because probably the parallax, the Hipparcos parallax, is introducing some problem here. It's indeed the main source of the uncertainty in the radius. So I redid basically these values with the Gaia parallax, and the difference is reduced significantly. So it's going in the good direction. But anyway, these are just details. What I wanted to present here is an idea about the technique we are using, and it's working very well. Well, then for the properties of the planets is straightforward. As I mentioned, from the light curve, you have a light curve from Brown et al. Torres et al. 2008, who used the light curve from Brown et al., but they did the analysis, and then they estimated the ratio of the radius of the planet versus the stellar radius. And also you can derive this light curve or this ratio from Spitzer, as was done by Evans et al. In 2015, and then you have very consistent values using any of these ratios, 1.41, 1.42. This is a radius which is relatively high if you try to explain with the planetary models, evolution models. You will have some difficulties I'm not an expert in this field, so maybe these difficulties are nowadays reduced significantly, but at least a few years ago when I read a few papers about that, it was a problem, no? Well, you have also the mass of the planet and the density, just combining all the measurements we had together with these ratios I mentioned. So this is pretty consistent with the literature, but I will not go into details. Just to briefly mention what is going to happen with Gaia parallax. Well, now we have the data release 1. You know that even some people have pointed out about possible systematics in the parallax. I'm not convinced about that, but anyway, it is probably better to wait till next year for checking the values with the data release 2. But as I pointed before, with the radius, linear radius you derive with Gaia, the value is closer to the evolution model, which means maybe not much, but well, it's just a fact. We have derived with this Gaia parallax, we have updated the absolute magnitude in V, and then the mass, and then log G. Anyway, using the absolute value of V and the color, you can redo the analysis with evolution models and infer somehow with lower uncertainties the values again. I didn't do because I don't think it's the purpose of this talk to present all these details here, but just, as I mentioned, to wait a little bit for the data release next year. And also we plan to present together with some data series of spectra that we have achieved a very good precision, and we will explain this technique eventually. I hope you will find interesting. So I will jump to the next part of the talk, where I am going to briefly explain why this technique is really useful in let's say, a general scenario with stars that have or have not planets around. So this is probably the data set you know, some of you at least, the next generation spectral library. It contains about 400 stars, well, 370 in particular, with a wide spectral range. And there are 78 type of stars that we use. And then we selected 28 of them because they pass a requirement, which is these residuals are really well constrained by these horizontal bars that you have at the level of 1 and 2%. So we constrain the deviations to basically 2% and got that 28 are very well fit by our models. Now again, the Kurucz models that I mentioned before. So this is a representation of 4 examples. Well, you have the very good results. And then, well, we can derive straightforward as we did for the host star, the planet host star. You can derive the effective temperature, the gravity, and the metallicity. And in green, you can see an example where the value for log G, for the surface gravity, is pretty similar to the one that you have already determined by the group that developed the library, no? NGSL. But you have other examples, and in red is the worst case, where the difference is not so good. Why did this difference? Well, think that for our exercise, we are getting the parameters for the best fitting. The resolution that I didn't mention, and now I think it's a good opportunity to say something about that, is just 700, which is not pretty good. So probably for log G is not the best scenario, and for the metallicity is also not so good. High angular resolution, high spectral resolution will be much better to derive the metallicities. So this is something we could point out. As I mentioned before, for the stellar angular diameter, this is not so important, because even if we are relatively far from the best solution, we are going to derive a pretty consistent value for the angular diameter anyway. But this is something we are working now on, no? So what is the difference between us and NGSL? Well, I mentioned how we determine our values. For NGSL, they use basically stellar structure models to determine the gravity. So we are somehow more confident with these values for the gravity. But this is something we are now researching and hope to get the conclusion quite soon. Well, then concerning the angular diameters, you have in blue the case of Vega. You have our value from CalSpec. 3 point, well, there are too many threes there, but it's real. So 3.333. Yes, interesting. And the error is 0.013. And the value by Aufdenberg from interferometry, as I mentioned, is just at the level of uncertainty of us. For brightest star, interferometry will beat our technique. And for fainter stars, although still bright, we have a better approach, I guess, as you can see there. No? For instance, the first example is 0.757 for us, and then in the literature you have two values for interferometry, and we are just in the middle of them. And the point here is that our value of uncertainty is certainly much lower than the interferometric values. Still consistent, but you know there is a significant difference. And for the second example, our uncertainty is like 5 times lower, and for the last one is well, about 2.5 or something like that. So there is a good agreement, but from the point of view of you know the precision, our technique looks pretty good and better than interferometry. There are only a few examples where we could compare with interferometric values because, you know, they are just, it is difficult to get, indeed, interferometric values. Well, this is just the series of publications we have done so far from 2010 to now, this year, with 2 publications. And as I mentioned before, well, we are still working on this, and I hope this introduction has been interesting for you. Thank you very much. Any questions?
Thank you, Carlos, for the interesting talk. And we have any question?
Yeah.
So you left us in suspense about phases. In 2013, is there any progress? Is it going to be flown, or what is happening?
No. It's a standby, I will say. It's difficult to arise. I mean, the budget is always an issue, right? And to convince about phases now, when you have missions like Plato, which is huge, and you can derive many things with Plato that you could do with phases, but just with, you know, little resources, probably is not so interesting anymore from this point of view. Phases could be rethought, no? In terms of, for instance, you could go to the ultraviolet or something like that, but it will be a completely different instrument, of course. But the idea is valid from many different points of view, but probably to materialize it now, as the concept that was done in 2009, I don't think is a convincing idea for me. But I will do, but you know, 10 million.
It's clear the work is very well worth doing. So if somebody does it, you can join them.
Somebody has the money, I will have a lot of engineering stuff done, no?
Good.
I have a curiosity, Carlos. So the end of your work is to find physical differences between stars with and without planets. I am not an expert on that, but how are you sure, 100% sure, that a star has no planet?
Well, I didn't put it this way, you know. If I catch your idea, you say that there may be differences between stars with and without planets. No. My aim is to characterize both groups. No, if you could find differences, you say, well, I don't think so. Probably, most of the stars have planets, although we don't detect them. So I don't expect the differences. What you may have are huge differences in the planets, just because of the differences in the stars, just because of the distance of the planet with respect to the star, and all this is a brand new discipline, no? Because astrobiology eventually will be developed hugely, probably with the James Webb Space Telescope and other similar missions, no? Where you are going to collect a lot of data to respond in this direction. But no, in general, the stars have properties that you may derive very fast, and then they are not very well ascertained, or you can derive carefully, and there is a huge impact in the context of exoplanets, just because many properties of the exoplanet are linked to the star. So you better derive very well the properties of the star, in particular the radius, as you have seen here, and then you have a better determination of the property of the planet.
Carlos, about an issue that shows up in exoplanets in transmission spectroscopy, and what you do in transmission spectroscopy is you compare spectra of a star during a transit of a planet against spectra when there's no transit. And you see small differences.
Right.
And these differences are caused by the occultation of the planet in front of the star. And usually what is observed is that there are wavelength dependencies, which are interpreted as different sizes, or that the planet has different sizes at different wavelengths, which is at the opacity or transmissivity of the atmosphere of the exoplanet. An alternative to this interpretation that it's purely the planet which we observe in these types of observations might be that the star also has an apparent radius that is somewhat wavelength dependent. And I wonder how far this might be observable with phases, or the type of investigations you're doing.
Well, this is something you can certainly do, because with phases, as you know, the difference with respect, for instance, Kurucz or Kepler, where you have just one band or 3 bands. Well, with 3 bands you can do already many things, but let's say with phases you can define your own filter band somehow, no? And play a little bit with that. Mm-hmm. Some people can tell you, why you don't do this in the infrared? Well, because the mission will be much more expensive, not less interesting. On the contrary, it will be very interesting in the infrared, near infrared, or in the ultraviolet, as I mentioned before. Well, phase was thought like an exercise to develop technically many things that I didn't mention in this talk, that's for probably different audience, no? Interested in engineering stuff. But concerning what you say, yes, if you define a filter, when you have a series of spectra rather than just a light curve in a certain band, you can study this possible problem, no?
Yeah, I mean, this is done from the ground a lot now, that you basically take light curves and you take them in spectra. So you have, for each wavelength you have a light curve, basically.
Right.
Or you have a transit event.
And if you have cosmic rays, you are not so affected.
Of course, you have all these cosmic rays you have in the space.
Have redundancy, and etc., etc.
But the issue is on interpreting these results, and there are some issues which are rather being discussed in the community. Is how far do these transit deaths, which we observe, which are planet sizes, how far does the wavelength dependency of these transit deaths really originate from the planet, and is not a feature of the stars? And I think that's where these absolute diameter determinations could come in, but wavelength dependent ones.
Yeah, exactly. That's another point. No, some planets that have been discovered are eventually fakes, just because this transit is due to a spot rather than a planet. No?
Yeah.
So spectroscopy is also a winner in this scenario, because you have much more information and you can certainly differentiate between both cases. So thank you for this comment, because it's quite rewarding for our faces somehow.
Okay, any other questions? Well, I remember you that at 11:30 we have the scientific coffee in the library. And Carlos, do you?
I think it's also very exciting to see that now we're using planets are being used to learn more details about the stars. I mean, it resembles also the case like in the sun, where we know the constant of the gravitational constant times the solar mass incredibly well, thanks to the planetary motions, right?
That's right. No, so basically everything is linked to each other. No, that's what is exciting about astronomy. And then because we don't know everything, we think things are isolated, but eventually, you know, they are quite linked to each other. If we know everything, we will see the harmony in the universe. It's very nice for the video conference.
Yeah, I wanted also to mention that Carlos is going to be here this week and next week, the entire week. So if anyone wants to talk to him, just write directly to him or to me, and we'll arrange a meeting.
You can do tricky questions during next week. You will see that I know little.
More time. Okay, see you at Scientific Coffee.
Thank you.
Thanks again.